Hey everyone, it's Bradley Bush with another algebra video for you. Today we are talking about radicals, understanding radicals, square roots, and nth roots, where n is a number 2, 3, 4, and on up. If this is your first time to my channel, welcome. If you're returning, thanks so much for coming back. I'd love it if you'd subscribe, leave a comment, or give me a like. Let's get going. Let's talk about principal square roots. So if we let a and b be non-negative real numbers, and if b squared equals a, then we can call b, which is the square root of a, the principal square root of a. So let's talk about an example here to make this a little more concrete. If we let b equal 5 and a is 25, then the question we have is, does b squared equal a? If it does, then b is the principal square root of a. So does 5 squared equal 25? And the answer is yes, it does. So we can see that 5 is the principal square root of a, and this is how we write it. We have this little radical symbol, and we have 25 underneath, and that equals 5. So we say 5 is the principal square root of 25. If we wanted to evaluate a bunch of these, we use this same property. So we can say that we're looking for something squared, right? Because remember, 5 was the principal square root of 25, and 5 squared equals 25. So is there something squared that equals 64? How about 8? We can rewrite 64 as 8 squared, and then we know now that d squared and the radical cancel, and we're just left with 8. 8 times 8 is 64. So 8 is the principal square root of 64. Here, we can do the same thing. 49, that's the same thing as 7 squared. We have this negative outside, so this 7 can come out now. The 7, or the square and the radical cancel, and the negative is still there. So the 7 comes out, and the negative is multiplied by the 7, so we get negative 7 there. So notice this negative was on the outside, not the inside. That's just like multiplying our answer by negative 1. How about this next one? The square root of 1 over 4. Well, we could say that 1/4 is the same thing as 1/2 squared, right? So we found something that we square and equaled 1/4, so that's our answer. The squared and the square cancel, and we get 1/2. How about the next one? What is 9 plus 26? Gives us 25. And we know from our past example that 25 can be written as 5 squared. And that tells us that 5 is the principal square root of 25. Perfect. How about this next one? Well, what's the square root of 9? 3 squared is 9. So that gives us 3 for the first number. And what do we have for the second number? It's so hard to choose a color. 4 squared, 16 is 4 squared. The square and the square root cancel, and we get 4 down here. And 3 plus 4 gives us 7. Interesting to see, though, that if we add the two numbers 9 and 16 together first and then take the square root, we get 5. But when they're split apart and the square root is taken separately, we get 7, which is a different number. So D and E are not the same problem. They're not equivalent expressions. We can't break up the radical with this plus sign and do them separately. So let's talk about a slightly different version of this same thing. This one perhaps is a little more mathematical. So if we let a be an element of the real numbers, so this little E-looking thing, it's an epsilon, it's a Greek letter, and it means an element of. That just means that a is a real number. If we let a be a real number, then we can define the square root of a as the square root of a squared, as the absolute value of a. And again, we're looking for the principal square root. So let's try this with our 25. 25 can be written as 5 squared, and then the a here is 5, so we have put 5 in absolute value, and absolute value of 5 is just 5. That was nothing new, right? That's really the result that we got a few moments ago. But let's try that with negative 5, because interestingly, negative 5 times negative 5 is 25, right? And 5 times 5 is 25. So if we wanted to find something squared that equal 25, we've actually got two options. We've got 5 and negative 5. But if we're looking for the principal square root, then this rule, the negative 5, is what goes into the absolute values, and the absolute value of negative 5 is 5. So the principal square root is always positive. If we wanted the negative one, then the negative would be out front. So that's how you know that they want the negative one. So if the negative is out front, like it was in the previous example, this 5 goes into the square root, and the square root of, the absolute value, and the absolute value of 5 is 5, and the negative out front just kind of hangs out and gets multiplied by the 5 at the end. If you have questions about this, please feel free to write them in the comments. Let's talk about principal nth roots. So n being 2, 3, 4, 5, and on up. So we're just making this generic. So before we were just dealing with square roots where n equals 2. But now n can be 3, 4, 5. You could have a 6th root. You could have lots of different roots here. And all of these roots are part of the radical family of functions. So instead of having squared for b, we have n, b to the n equals a. And then we call b equals the nth root of a. We call that the principal nth root of a. If n is even, like a square root is because n's 2, then a must be non-negative and b must be non-negative, meaning positive or 0. If n is odd, then a and b can be any real number. Positive, negative, doesn't matter. So here's the rule. If n is odd, then the nth root of a to the n is just a. Doesn't matter if it's positive or negative. So if we look down here, n is odd in this example, and we have the cube root of negative 2 to the 3rd power. The 3's, the 3 in the index on the radical and the 3 in the exponent cancel, and we're left with negative 2. It's okay. It can be negative. The result of an odd indexed radical can be negative. And the index, by the way, is this number. Maybe I should write that. The index of a radical is this number where the n is n. N is the index of a radical. So maybe I'll put an arrow to these n's as well. If n is even, then we have the same rules we had before. The nth root of n is the absolute value of a. So the nth root of a to the n is the absolute value of a. And we can see an example of that here where we have n is even, n is 4. We have the 4th root of negative 2 to the 4th power. The negative 2 is what goes into the absolute value, and then the absolute value of negative 2 is just positive 2. And that's our answer. So the even indexed radicals have positive results, and odd indexed radicals can have positive or negative results. Let's look at some properties of nth roots. Again, n can be 2, 3, 4, on up. The first property is that if we have the nth root of a times b, so we have two things multiplied together underneath a single radical, we can separate those two into two separate radicals being multiplied together, but they both have the same root, the same index as the original. In this case, it's n. So our example, if n equals 2, then notice if n equals 2, it's the default, and we don't write 2. So if you see a radical symbol that doesn't have an index, you assume it to be 2. We can rewrite this using our rule. I just put an equal sign twice there. I didn't need to do that. The 4 and the x are two things multiplied together, right? So we can split this up and do the square root of 4 times the square root of x. What's the square root of 4? 2. So that just gives us 2 times root x. And the second one, we can go the opposite direction. We can combine. We have two things multiplied together, and we notice that the index on both of them is the same, so we can combine the insides. So if we do that, we have 8 times 4, and this is the fifth root. Fifth root of 32. Fifth root of 32. We can rewrite 32 as 2 to the fifth power, and that just gives us 2 because the 5 and the 5 cancel, and we get 2 out. Our next property is a quotient property. The first one was multiplication. This is a division property. So we notice if we have something like a divided by something like b, and by the way, b cannot equal 0. I probably should mention that in this case, or we would have 0 in the denominator, and we can't have that, right? So if we have a divided by b, we can split that up into two separate radicals with the same index as the original. So if n equals 4, and we have the fourth root of 81 over 16, then we could split that up into a couple different radicals. So we have the fourth root of 81 divided by the fourth root of 16. What is the fourth root of 81? 81 is the same thing as 9 times 9, and there's 2 3s in each of those 9s. That helps us. So really 3 to the 4th power. There. How about 16? 2 times 2 is 4. 4 times 4 is 16, so there's 4 2s. Whoops. So we have some cancellation then. The 4s can cancel, and we're left with 3 in the top, and in the bottom the 4s cancel, and we're left with 2 in the bottom. So we get 3/2 as our answer there. We could also, so in the first example we split them up. In the second example, here n equals 3. We have 3, we split them up. We have them split up there. We can put them together as 128 divided by 2, and that's all over the cubed root. 128 divided by 2 is 64. And we have the cubed root here. What's the cube root of 64? Well, we have 4 to the 3rd power. Gives us 64. So the cube and the cube root cancel, and we're left just with the 4. I should make a note here. Technically speaking, I skipped over something that you might skip over too, and most of the time it's okay, but I just wanted to clarify to make sure you guys saw what was happening. So I need a different color to do this in that I haven't used. How about I use this gray? So because n right here was even, this technically, the square root of 4, technically was absolute value of 2, which is 2. The answer didn't change. It still was positive, but just wanted to make sure you guys noticed that. Because n is odd here, we don't have the absolute value. You guys remember this rule right here? So I just wanted to make sure you guys you saw that I was doing that. I just did it in my head. Here, the last one, n equals 4, we have that same thing going on. Technically here we have absolute value of 3 over absolute value of 2. Those are both positive to begin with, so it didn't change the answer. We still got 3 over 2. Just wanted to clarify. All right, let's talk about adding and subtracting radicals. We add and subtract radicals in a very similar way that we add and subtract polynomials. If you remember adding and subtracting polynomials, you only add and subtract polynomials if they are like terms. So for example, 3x and 2x, that means we have 3 of these x's and we've got 2 more of those x's, and if we count them all, we've got 5, because 3 and 2 give us 5. It's like we've got, 3 oranges and 2 oranges. How many oranges do we have? 5 oranges, because we had the 3 oranges and the 2 oranges. But we couldn't add together an x and an x squared because they weren't like terms. They have the same variable, but they don't have the same exponent. So we just have to leave it separate. Radicals are very similar. If we have a radical 6, a square root of 6, and we've got 3 of them, if we have 2 more radical 6's hanging out, we can add the 3 and the 2 and get 5 radical 6's. But radical 6 is just like an x. You can only add other radical 6's to it. So if I had a radical 6 here, I have the square root of 6, and I've got 3 of them. And I have over here square root of 5, and I've got 4 of them. I can't add them together because I can't add the square root of 6 and the square root of 5 because they're like apples and oranges. They're like x and y. Or they're like x and x squared. They're not the same radical, so I can't add them together. They're not the same thing. So that's pretty straightforward. Let's discuss. Let's do some examples. So if we have 8 radical 13s, or 8 square root of 13s, and we have 9 square root of 13s, we add them all together and we get 8 plus 9 is 17 radical 13. That's nice, huh? In the next one, we have 15x underneath the radical. It's the 4th root of 15x, and then we take 12 of them away. Well, we're kind of in the hole, aren't we? We have 15x in the 4th root, so they're the same radical. And if we have 1 minus 12, we get negative 11. And we still have the 4th root of 15x. Let's combine some others. We may need to simplify these first. That's something you should look at, and I'm sure you'll see that if you're doing homework problems like this. These two are not the same radicals. So we have square root of 27, we have square root of 12. So when we first look at it, we think, hey, we can't add these. But can we simplify both of those radicals so that we do have the same radical? Well, let's look at the 12. How can we rewrite the 12? We can rewrite that as maybe 3 times 4. And the 4 could come out. How about the 27? Can we rewrite that? How about 9 times, or 3 times 9? Notice in each of these, the 9, oh, you can't even see that. The 9 can come out of the 27 and the 4 can come out. Let's try this. This might work for us. We have 5 here, and we have a radical, and let's say, let's split these the 3 and the 9 up. That gives us 27 is 3 times 9, so we have the square root of 3 there, and we have the square root of 9. And then the 12, we have the square root of 3. We're splitting these up, and the square root of 4. We know that this is 3. This is 2. So let's put those out front. So 3 comes out front, multiplies by the 5, and gives us 15. So we have 15 root 3. That's not a very good 3, is it? And then we have a 2 that can come out in front, and we get 2 root 3. Now we have 2 root 3s. So we have 15 root 3, and then we have 2 more root 3s. Now they're the same radical, and we can add them. So 15 and 2 is 17. So we have 17 root 3. And that's our answer. How about this next one? Let's see, we have the square root of 18x. We've got 6 of them, and we are trying to take away 4 root 8x, or square root of 8x. So 18x and 8x are not the same thing. Can we fix that? Can we simplify them? I think that we can, because this really could be written 6 root, let's say 9 times 2x. The 9 can come out, right? This next one can be 8 is the same thing as 4 times 2x. And the 4 can come out. So we can take this 9 out, and we can take the 4 out. So let's keep working on that. Let's do that. Let's split these up. We have 6 multiplied by root 9 times root 2x minus 4 and root 4 times root 2x. This is nice because we know that the square root of 9 is 3. The square root of 4 is 2. So this plays out kind of nice, right? 6 and 3 give us 18. And then we have root 2x. And we have 2 times 4 is negative 8, which times root 2x. And we now have the same radical, right? So we can now subtract them. We have 18 of these 2x's, and then we take 8 of the 2x's away, which gives us 10 root 2x. Fantastic. Again, if you have comments, please, questions, please leave them in the comments. Here we go. Here's our last one. Let's combine these. We have the cube root of 16 and the cube root of 2. Well, those aren't the same thing, but can we make the cube root of 16 into a cube root of 2? I think it's possible because what is 16? What is, how about this? 16 is 8 times 2. And the cube root of 8 is 2. So that'll come out. This is going to work great. Let's keep going here. We have 5, and we can rewrite this as the cube root of 8 times the cubed root of 2. And we have minus 11 cubed root of 2. Cubed root of 8 is the same thing as 2 because 2 cubed is 8. So this gives us 2 times 5, which is 10, times cube root of 2 minus 11 times cube root of 2. We've got, now they're the same thing. We've got cube root of 2 in both places. We have 10 on the left and we subtract 11 on the right. So that just gives us a negative. We have 10 minus 11 gives us a negative 1, right? And negative 1 times cube root of 2 is just negative cube root of 2. We're done with that. Our last one. Let's see, we've got the cube root of 81, and we have the cube root of 3. Well, we can't do much with the cube root of 3, but can we make the cube root of 81 into the cube root of 3? 81 is the same thing as 9 times 9, right? And 9 is 3 squared. So this is 3 times 3 for the first 9, and then 3 times 3 for the second one. So if we take the 3 of the 3's, that gives us 27 times 3. That's going to work out. So we have 3 here, and then we have cubed root of 27 times 3. That's going to be perfect. We can just bring down this one, 4 and cube root of 3. We know that we can rewrite this as 3 and cube root of 27 times the cube root of 3. And then we have the negative 4 times the cube root of 3 still hanging out. We know cube root of 27 is 3. 3 times the 3 in front give us 9. So we have 9 times the cube root of 3. And this cube root of 3 is the second one there in the picture. Almost done. We can subtract now the 4 from the cube root of 3. And we're good, right? We have cube root of 3 in both spots. We have 9 cube root of 3 on the left, and we're subtracting 4 cube root of 3. 9 minus 4 is 5. So we have 5 cubed root of 3. And we're done. Hopefully this was helpful. If you have questions or comments, please feel free to leave them in the comments below. Thanks for watching. Have a good day.